Hello everyone. Introduce my name is Party Rosiad on Pero's Cement Techno channel. On this occasion I will explain about the development of cement factories in Indonesia and the development of cement production process technology. Cement industry development in Indonesia. In 1910, the first cement factory was built in Indonesia by the Dutch East Indies government, precisely in Inderung, Padang, West Sumatra. The first unit Semen Padang factory with a wet process production capacity of clinker 200,000 tons per year, and currently Semen Padang has 5 operating units with a capacity of 8.5 million tons of clinker per year. The wet process Inderung Unit 1 is no longer in operation. In 1957, the Gresik cement factory with a wet process capacity of clinker 250,000 tons per year was built in Gresik, East Java. In Gresik there are 4 unit factories, and in 1994, Gresik Cement expanded the plant to Tuban district with 4 unit plant. And in Rembang district in 2016, 1 unit plant. Currently, Gresik Cement with a total capacity, 11.9 million tons of clinker per year. Meanwhile, the Gresik factory which uses the wet process, is no longer in operation. In 1968, the Tonasa Semen plant with a wet process capacity of clinker 120,000 tons per year was built in Tonasa, South Sulawesi. Currently, Semen Tonasa has 4-unit operating plant with a clinker production capacity of 5.98 million tons per year. The Tonasa Unit 1 with the wet process is no longer in operation. In 1973, Indocement with the Tiga Roda brand started to build a factory in Sidrap, Bogor, West Java. And the first factory started operating in 1975, with a clinker production capacity of clinker 600,000 tons per year. Currently, Indocement has 13-unit plant located in 3 plant locations, namely, in Sidrap Bogor, 10 units factories, in Cirebon, 2 units factories, and in Tarjun, South Kalimantan, 1 factory unit. Clinker's total production capacity equals 18.6 million tons per year. And Indocement has a factory that specializes in producing white cement. In 1974, the Baturaja Cement Factory Unit 1 was established in Baturaja Jambi, with a production capacity of clinker 550,000 tons per year. Then in 2001, it was optimized to 1.25 million tons per year. Baturaja Factory Unit 2 started production in 2017 with a capacity of 1.85 million tons per year. In 1975, the Cibinong cement plant with the Kajang brand, Unit 1 with a clinker production capacity of 600,000 tons of clinker per year, began operating in Narragong, Bogor, West Java. In 1977 Semen Cibinong acquired Semen Nusantara Silicap, and in 2006 officially changed its name to Holcim Indonesia Tbk. Holcim Cement has 8 factories in 3 locations, Holcim Narragong 4 factories, Holcim Silicap 2 factories and Holcim Tuban 2 factories. Total clinker production capacity, 14.7 million tons per year. And currently Holcim Semen has joined the Semen Indonesia group under the name SBI or Semen Bangun Indonesia. In 1980, the Kupang cement factory was built in Kupang with a upright furnace or shaft kiln with a production capacity of 120,000 tons per year. Since 1996, Semen Kupang, which uses upright furnaces, has ceased to operate, and in 1997 built a new factory unit rotary kiln with a production capacity of clinker 330,000 tons per year. In 1982, the Andalas cement factory was built in Aceh, with a clinker production capacity of 1.6 million tons per year. And in 2004 the factory was badly damaged by the tsunami, then after being reconditioned by Lafaz Semen and only started operating again in 2010. Currently Semen Andalas has joined the Semen Indonesia group under the name Semen Bangun Andalas. In 1999, the Bosowa Cement Plant Unit 1 was established in Maros, South Sulawesi with a clinker production capacity of 1.8 million tons per year. And in 2014 a factory Unit 2 was built with a clinker production capacity of 2.5 million tons per year. In 2011, the Juishin Indonesia cement plant under the Semen Garuda brand started operating in Karawang, West Java, with a clinker production capacity of 1.6 million tons per year, In 2014, the Conch Cement Indonesia factory built 2 units of factories in Tanjung Tabalong, South Kalimantan, with a clinker production capacity of 3.2 million tons per year. In 2015, Cemindo Gemilang cement factory, with the brand Semen Merah Putih, began operating in Baya, Banten, with a clinker production capacity of 3.3 million tons per year. In 2015, the Siam Cement Group cement factory, with the brand Semen Jawa, started operating in Sukabumi, West Java, with a clinker production capacity of 1.6 million tons per year. In 2015, the Bima cement factory started operating in Ajibarang, Central Java, with a clinker production capacity of 1.6 million tons per year. In 2016, the Indonesia Papua Conch cement plant began operating in Maruni, West Papua, with a clinker production capacity of 1.6 million tons per year. In 2020, the Grobogan cement plant began operating in Grobogan, Central Java, with a clinker production capacity of 2.5 million tons per year. Now we will explain about anything, types of cement production process. The cement production process, when viewed from the water content of the raw feed, consists of 4 types of processes, including 1. Wet process, 2. Semi-wet process, 3. Semi-dry process, 4. Dry process. This is one of the sample images on wet process. The raw material is fed into the rotary kiln, in the form of slurry with a moisture content of 25 to 40%. In general, this process uses a long rotary kiln, with the initial heat transfer occurring at the kiln inlet. This type of process is very energy intensive, because the heat consumption used is, not only for the clinker formation process, but also for evaporating the water content in the feeding kiln. The heat energy consumption ranges from 1500 to 2000 kilocalories per kilogram of clinker. The form of the equipment or machine used is still very simple. The residual gas from the combustion inside the kiln exits through the dedusting cyclone near the kiln inlet and is directly discharged into the chimney, where the temperature is still high, between 200 to 250 degrees Celsius. The production process of this type of cement uses a kiln dimension which is long divided by diameter is 33. The advantages of this process are better mixing and correction of raw feed material composition. The kiln feed material, which is sticky and plastic, does not cause significant problems. And this is one example of the semi-wet process. The kiln feed material is in the form of nodules or pellets, which are made with the help of a filter press whose kiln feed water content ranges from 15 to 25%. Kiln length in this process is shorter than in the wet system process, while the heat consumption used for the clinker production process ranges from 1000 to 1500 kilocalories per kilogram of clinker. And this is an example of a semi-dry process. In this process, the raw feed is in the form of dry flour, which is fed into a pelletizer, then sprayed with water to form granular, and the water content is between 10 and 12%, with a size between 10 and 12 millimeters. Then the material is fed into the rotary kiln through the drag chain in the preheater. The heat consumption in this process is, generally, around 1000 to 1200 kilocalories per kilogram of clinker. Next, for the dry process. The high consumption of heat used for the cement production process in the wet process, semi-wet process, and semi-dry process, the cement factory makers are trying to find other possibilities and ways, in conducting pre-blending and homogenizing the kiln feed in a dry state, or water content between 0.5 and 1%. Pre-blending of raw feed or raw meal is started in the process of grinding the raw materials, then blending the raw meal is done in the silo, by stirring using aerated air, until the quality of the raw meal composition is as desired. Then, the raw meal is suspended into the preheating system, which then enters the kiln. This preheating system is vertical and stratified, with a fairly high temperature, so that a decarbonization reaction occurs between 30 to 40% for conventional suspension preheaters. Cement production process using suspension preheater can increase the clinker production capacity, which is higher compared to the previous process, and the heat consumption is between 800 to 1000 kilocalories per kilogram of clinker. Preheater system. To increase the production capacity of clinker and reduce its heat consumption, NSP or new suspension preheater was found, or conventional preheater with added calciner burner, which was installed with a preheating system with the aim of increasing the degree of calcination to more than 80%. There is an increase in the degree of calcination in the higher preheating system, so the decarbonization process in the kiln is less, and the fuel consumption in the main burner can be reduced, so that the refractory bricks in the kiln are more durable. After the discovery of the new suspension preheater, which is proven to be very effective and efficient for the cement production process, almost all cement factory makers are competing to develop and begin to abandon the development of the three previous processes. In the development of the suspension preheating system, each cement manufacturer has a different design, but has the same goal, namely increasing the degree of calcination and increasing clinker production capacity and reducing the consumption of heat energy used. The idea of making a raw meal preheater system has existed since the 1930s, and when viewed from the principle of heat transfer there are two kinds. 1. Countercurrent, material is fed from the top and hot gas flows from below. The disadvantage of this method is that the contact time of the material and hot gas is very short, making it less efficient. 2. Co-current or direct current, this system generally uses long ducting and uses a multilevel cyclone. The material flow is fed to the top cyclone inlet duct and then simultaneously meets hot gas from below. With this system the contact time of the hot material and gas is longer and more efficient than the countercurrent. Preheater system with direct flow was first introduced in 1951 by F. Muller from KHD. With a material separation system and hot gas cyclone type 4 stages. Here are some multilevel cyclone type preheater systems made by some of the world's well-known cement manufacturers. Type of suspension preheater system. These are sample images of the preheater system with a 4-stage cyclone. Figure 4. Direct current preheater system developed by KHD. Figure 5. Preheater system combination of countercurrent and direct current developed by Pelagius. Next image, Figure 6. Preheater system with vortex developed by Humboldt-Wedag, Germany. Figure 7. Preheater counter-flow combination system on the lowest preheater, soft preheater, developed by Mayag. Next picture, Figure 8. Preheater system with counter-flow, developed by Krupp and applied by Pelagius, which was named Jeppel, Gegenstrom Warmer Tauscher Pelagius. Figure 9. Pelagius also developed a unidirectional flow system, called Dopal, Doppelstrom Pelagius. Precalciner or NSP or new suspension preheater. NSP is a development of the suspension preheater which is equipped with a calciner or combustion preheater. It was first applied by the Humboldt-Wedag Company in 1966. Then since 1970, the trend has been to build cement factories with large capacities using the precalcining system. The advantages of using precalciner over conventional SP are: 1. The degree of calcination in the precalciner can reach 85 to 95%, which in the conventional suspension preheater is only 30 to 40%. 2. Can increase the production capacity of a larger clinker. 3. The use of fuel in the main burner is lower, so that the life of the refractory bricks in the kiln is more durable. 4. Kiln operation is more stable and easy to control. The disadvantages are: 1. Higher pressure drop than conventional SP. 2. Temperature outlets tend to be higher. Precalciner system development. Each cement manufacturing company has a different design in developing the precalciner system, but with the aim of increasing production capacity by optimizing the combustion process and material separation in the preheater system. When viewed based on the air supply for the combustion process in the precalciner can be divided into two types including: 1. Air through, or air directly from the kiln, that is the combustion air for the precalciner system obtained only from the air remaining from the combustion process from inside the kiln. 2. Air separate or separated air, namely combustion air for the precalciner in addition to the air remaining combustion process from inside the kiln. It's also taken from the cooler or secondary air and flowed through the tertiary air duct to the calciner. Of these two types of precalciners, the air-through system has not been developed much, because the combustion process in the preheater is not optimal. While the air-separate system, that uses secondary air from the cooler has been proven to improve the combustion process in the precalciner, and can be increased the degree of calcination to a higher, the type of air-separate is more widely developed by all cement manufacturing companies. Example drawings of air through precalciner system types. Precalciner system air-through. In this type, the combustion air in the calciner burner only relies on the remaining air from the internal process in the kiln. The disadvantages of this type are, 1. The combustion process in the precalciner burner is not optimal, because only 30% to 35% of the total fuel can be used. 2. The use of fuel in the kiln is more, which is between 65 to 70% of the total fuel used, so that the life of the refractory bricks in the rotary kiln is not durable. And this is an example image of the air-separate in-line calciner precalciner system. Figure 11. Precalciner system in-line calciner, developed by Humboldt-Wedag, Germany. Precalciner this type, in addition to taking combustion air from the kiln, also utilizes secondary air taken from the cooler, which is flowed through the tertiary air duct for the combustion process in the calciner. There are two types of air-separate precalciners, including 1. Inline calciner. 2. Combination of inline calciner and separate line calciner. Furthermore, this is an image of the combination precalciner between ILC, inline calciner, and SLC, separate line calciner, developed by F. L. Smith. Separate line calciner of this type, the combustion air for the calciner SLC only takes secondary air from the cooler, and the fuel consumption in the SLC burner can reach 55%, the fuel in the ILC is 10%, and the fuel in the main burner is between 35 and 40% of the total fuel consumption. Because the use of fuel in the main burner kiln is less, the life of the refractory bricks in the kiln is longer than the previous type of precalciner system.
Development of ILC and SLC precalciner systems. Air-separate precalciner combination of ILC and SLC developed by F. L. Smith proved to be able to increase production capacity twofold when compared to ILC precalciner. By using this system, the production capacity can be increased to 7,500 to 10,000 tons of clinker per day. This success was also followed by several other cement manufacturing industries, such as Kawasaki with KSV, Kawasaki spouted bed vortex chamber, the production capacity of which was reached 9,400 tons of clinker per day. Likewise with other Japanese companies making RSP, reinforced suspension preheater. The degree of calcination reaches 90 to 95%, for this type the fuel consumption in the calciner is between 55 to 70%. And the fuel consumption in the kiln main burner ranges from 30 to 45%. The combination ILC and SLC precalciner was also developed by Mitsubishi Heavy Industries, under the name MFC, Mitsubishi Fluidized Calciner. By applying the precalciner combination of ILC and SLC, besides being able to increase production capacity, the heat consumption used is very low or less than 700 kilocalories per kilogram of clinker, and the average SP top temperature is less than 360 degrees Celsius. To reduce the SP's top temperature, the preheater system was developed by adding the cyclone level from 4 levels to 5 levels, and there are 6 levels of cyclones. Conclusion. In the development of cement industry technology, the development of the cement industry starts from low capacity with high heat consumption, especially in the wet process. Then, it was developed with a preheater system for dry processes, starting from suspension preheater, and the addition of a calciner burner with an air-through system without tertiary air duct, and further developed with air-separate calciner with secondary air from cooler through tertiary air duct. Further development of preheater system, inline calciner and separate line calciner, and the preheater system was developed by adding the cyclone level from 4 levels to 5 levels, and there are 6 levels of cyclones, so that the clinker production capacity is getting bigger and heat consumption and power consumption are getting lower. Thank you for watching this video. Don't forget to subscribe, like, comment, and turn on the bell, so you don't miss the next latest video series.